Hello physics students. So what I want to do is show you a couple fun demonstrations that are not really part of the curriculum but are important for their practical consequences and in terms of understanding things like how our electrical grid operates. So we've seen this already when we were talking about Faraday's law and induction. When I plug this in, I get the light bulb to turn on, and the reason why is because what I have is an alternating current in this coil. It oscillates back and forth, which creates an oscillating magnetic field, which then oscillates through this coil, creating a changing flux, which according to Faraday's law, right here is the definition of flux. So with the magnetic field oscillating, the flux oscillates, and then therefore by taking the derivative of that, we see that there's a voltage that will oscillate, and so we get alternating current in this top coil. However, something that you may not have realized is that what I'm really doing is I am transferring electricity without electrical contact with only magnetism, and in the process what I'm doing is I'm changing the voltage. If I poke this tiny bulb directly into a wall outlet, it's too much voltage, the light bulb would burn out. Nothing dramatic, might just flash for a second and go dark, and the bulb is, garbage. But when I transfer the electricity through the two coils linked magnetically, the voltage of 120 is reduced to an amount that's safe for the bulb, and the bulb glows nicely without burning out. So what I'm doing is changing voltage through magnetism. And that brings me to the important principle. The topic for this video is how a transformer works, what a transformer is. Remember when we were studying earlier in the year, when we were studying power, I showed you a clip of these workers working on these high voltage power lines going from maybe one side of the continent to the other, delivering electricity from the power plant to maybe like a city. And these wires were such high voltage, they were like 700,000 volts, such that the people working on them could not put a ladder up to the wire because the electricity that would go through their body and into the earth would be so large it would basically vaporize them. So what they had to do is be delivered to the power lines on a helicopter isolated from ground. But the point is, these voltage wires bringing voltage from the power plant to the place where the customers need it was like 700,000 volts. If you were to put that into a house, it would create lightning bolts all through the house and catch it on fire and burn it down very quickly and kill anybody inside. So they have to figure out a way to get that voltage to get reduced to a safe amount. And that's where the transformer comes in. You may have seen a transformer on a telephone pole, not knowing what it was. They're these like cylindrical objects. They look a little bit like maybe like a garbage can at the top of a telephone pole. So that is a transformer. What do they do? Well, let's take a look. Let me just reconfigure the camera. I have a smaller transformer here so you could see how it works. So here is just a simple transformer made for a classroom, and what you could see hopefully are two coils here. One is called the primary, one's called the secondary, and they're linked through with iron so that they're linked magnetically. And the nice thing about this is that we could take it apart and study how it works. So this coil, I'll bring this up to the camera, and hopefully you could see, well, you could see the writing. It says 800 turns, and if you look closely, you can see the wire spiraling around this rectangular block from one side to the other. It goes around this block 800 times. That's why it says 800 turns. And then there's this iron passing through this coil, and then when I put this on top, it links the two pieces of iron so that the magnetic field that comes through this coil will then go and be piped through this second coil. The second coil, this one, you see the wire is much more crude, so you could right away see there's less wire turns here. It says 80 on there. And it says also 12 volts, so we'll see that and we're going to measure that. So fewer turns, a lot of turns of wire, not many here. And what I'm going to do is go like this, hook it all together, and then I'm going to plug this into the wall. And so the reason why is we need alternating current. Transformers will not work with direct current because what will happen is there'll be a constant magnetic field in this coil, and therefore a constant magnetic field in this coil. There will be no voltage transferred from one coil to another. So transformers cannot work with like just regular old battery power. So that's how do you say, we thank Nikola Tesla for his invention of alternating current. This is one practical aspect of it. So I'm going to plug this in now. And so we're going to say it's not a big deal. That's just the magnetic field causing vibrations. So what I'm going to do is measure the voltage in the primary coil. And let's see, is there glare on this? Let's see. Okay, so I go here. This is the primary coil voltage, and you see 120 volts on the voltmeter. And of course, you know that because the wall outlets, as I've mentioned many times in the class, are 120 volts. Now, this had 800 turns, 120 volts going through it. This only has 80. Notice there's a 10-to-1 ratio, 80 to 800. Fewer coils here. Let's see what we get for voltage up here. And we get around 13, pretty close to 12, right? So that's the 10-to-1 ratio. We have 1/10 the coils, and we end up with about 1/10 the voltage. So let me just do one more different coil here. So this one, instead of 80 turns, what I'll have is this one, which has 200 turns. So we're going to have 800 down here and 200 here. Notice we have a 4-to-1 ratio, or 1-to-4, however you want to say it, and you'll see the same kind of relationship with the voltage. So this time with 1/4 of the wire turns, we still have 120 here, right? You see that? But here, now we're going to have about 30, which is 1/4 of the 120. So 1/4 of the coils, 1/4 of the voltage. That's how a transformer works, or what it does. Now, what's the physics behind this? Well, here we are, transformer. What we can say is that the magnetic flux going through this iron is constant because you could think about some magnetic principles, but whatever magnetic field comes out of this coil gets piped around here. So they have the same ultimate magnetic flux going through the iron. But on one coil, the first coil, the total flux is the magnetic flux in the iron times how many wire turns there are. Because there are 800 turns here, the total flux will be 800 times the flux in the iron. And on the other coil, the secondary coil over here, the total flux will be the total number of wire wraps here times the flux in the iron. Now, again, the flux in the iron is the same in both coils. So what I can do is solve for the flux in the iron right here, which is flux 2 over N2, and plug that into flux 1 expression, and I got rid of the flux iron right there. And now what I have is a relationship here between the two fluxes in the two coils. And if I take the negative derivative of both sides, why would I want to do that? Because as we know from Faraday's law, if you take the negative derivative of flux, it's the voltage in the coil. So as you can see, the negative derivative of the flux here is the nth in coil 1. The negative derivative in flux in coil 2 is the voltage in coil 2. And then here are the n's here. And then you get the simple ratio M1 over N1 equals M2 over N2. So for example, we had 120 over 800. And then over here we had, instead of 800, we had 80. So we only had 12 to preserve that relationship. So if you want to copy these down, you can. It's not necessary. It's not part of the curriculum. Alternating current is not part of the curriculum. But if you're interested in these things, go ahead and jot it down for future reference. Okay, so what I want to do is maybe show you just another cool thing that's kind of irresistibly fun, but again, not part of the curriculum. So hold on, let me reconfigure the camera. All right, one last one, but I will mention that there are some other really cool ones where you could boil water here, create steam through the inductive effects. You get a lot of current in this metal here and eventually heats up and boils water. That's kind of nice, but this one is a lot of fun. What I'm going to do is turn this on. What I have here is just an aluminum ring around here, and you'll see when I turn this on, it shoots the coil up. One more time. And the reason why that happens is we've got an induced current which creates its own magnetic field which starts interacting with this magnetic field. But the true picture of that is beyond the course, because if you just look at this in a simplified manner, sometimes these magnetic fields cause a repulsion, but sometimes an attraction. To really understand this, you've got to understand something like called a phase lag in the current in this top coil, beyond the curriculum, but still a lot of fun to see. One more time, usually I get it to hit the ceiling, so let's see if it'll go this time. All right, maybe not. All right, well, thank you for joining me again. I hope you enjoyed these little fun demonstrations, as well as the explanation of how a transformer works. I'll see you in the next physics video.